Hello everyone, welcome back to my channel. Today we're gonna go over this problem of control systems, and control systems is very important in a lot of regulating a lot of devices. And this problem specifically deals with statistics. So let's read the problem statement first. A batch of 1 billion resistors is known to have a normal distribution of resistance values of standard deviation sigma r is equal to 9 ohms. The 95 confidence interval for the average resistance of the resistors mu r is to be determined by measuring several resistors. Assume the millimeter measures exactly. From the list below, what is the fewest numbers of resistors that should be measured to determine the average resistance of the batch to within plus or minus 1 ohms with 95% confidence? So first, let's break down this problem. What is this problem asking us to find? Well, we know that the batch of resistors has a normal distribution, and in statistics, a normal distribution looks something like this. Let me try it. Yes. So in statistics, a normal distribution looks something like it's also called a Gaussian distribution. Means that their values are relatively even distributed, and 95 confidence interval is usually over here, 95% confidence interval, and assumes that the multimeter measures exactly. So what is the fewest numbers of resistors that should be measured to determine the average resistance of the batch to within plus or minus 1 ohms with 95% confidence? So basically, they want us to measure it to a value of plus or 1 uh, negative 1 or plus ohms or plus or minus 1 ohms basically. So let's go look at the concept of confidence interval. So this is the expression for confidence interval. Basically, when sampling from a normal distribution with known population standard deviation sigma, the 95% confidence interval for the population mean mu is equal to this, where x is equal to the sample mean, z is the z-score corresponding to the desired confidence interval, and sigma over root n is the standard error of the mean. So basically, in our case, it is plus or minus 1 ohms, and x is the mean of our normal distribution. So yes, it's the sample mean, and yes. And in our case, this applies because we have a batch of 1 billion resistors, so it has a normal distribution. Um, and here we have the 95% confidence interval for the average resistance of resistors. So basically, the average resistance of resistors is mu r, which corresponds to x bar in our general equation for for confidence interval, which is the mean plus or minus sigma over root n times the z-score, as we saw earlier. So we want to determine here what n is, or the fewest number of resistors that should be measured to determine the average resistance of this batch to within plus or minus uh, 1 ohms with 95% confidence. So basically, the plus or minus part is the margin of error E, and the margin of error is the amount by which the sample mean can differ from the true mean uh, at the given confidence interval. And this is the formula you see. And we can rearrange to solve for the sample size n. And if you want your estimate to be within a specific accuracy E, you can rearrange to solve for n. And this formula tells you how many samples you need so that your sample mean will, with the specified confidence interval, be within plus or minus E of the true mean. Where z comes from, so for a 95% confidence interval, z comes from a z table. And basically, because 95% of the area under the standard normal curve lies between negative 1.96 and plus 1.96. That is why. And here's a summary of the key concepts. The confidence interval equation might be expressed in other different ways too, like this equation over here. So don't get confused, um, because this one is basically saying the same thing. This one is the sample mean, I believe. Or I guess it's actually the population mean, and then this one is the sample mean. And then this part is our E value, which is the confidence interval at 95%. Yes, so basically, the 1 billion resistors, I'm guessing, is our population, and this population is normally distributed, and the standard deviation is 9 ohms. And the 95% confidence interval for the average resistance of the resistors is to be determined by measuring several resistors. So this over here is going to be our sample size. Assume the multimeter measures exactly. So what is the fewest number of resistors that should be measured? So what is the smallest sample size that we should take? In other words, to determine the average resistance of the batch. So what is the fewest number of resistors that we should measure as our sample size in order to determine the population mean or estimate the population mean to plus or minus 1 ohm of the real population mean. And with 95% confidence, we can say that this is probably what the population mean is. And so, and this one is equal to the population mean, which we will call oh wait, sorry, or over here. We will call this X bar, shall we? Yeah. So basically this portion over here corresponds to our sigma over root n over z. And sigma is given to be 9 ohms. And n is what we're trying to find. And z is the z from the z table at 95% confidence. So let's find what that z value is. So here's the z table. And basically, you want to find the value at a 95% confidence interval. So how to use a z table is 95% means 0.9. And then you look to, okay, so we want in this column. And then 0.5 is right over here. So this value. So it'll be 0.6579. So then 1 is equal to 9 over root n times 0.6579. And solving for n, we find that n is equal to, oh, sorry. So I actually found the z-score wrongly. Um, so basically we have to know what 95 confidence interval means. 95% confidence interval means that 95 percent gives us the area under this curve. So the area under this curve is 0.95, and the total area under this Gaussian distribution is 1. So we actually have to work backwards. We are not given a z-score. We are given error, but we want to find z-score. So we have to look for a value close to 0.95. So that value will be between, oh, that value will actually be exactly the 0.95, which is at a value of Uh, okay. First we have 1.9, and then over here we have 0.06. So 1.9 plus 0.06 is equal to z. So our z-score is equal to 1.96. So here we plug it in 1.96, and now we solve for n. So n is equal to 9 times 1.96 divided by 1 and square that, which will give us 312. I, around that value. Yes, we actually got n is equal to 311.1696. But we always take the ceiling of this value, which means that even if this value is 1 and it will usually round down to 311, we play on the safe side and we round up to 312. So that is the correct answer. I hope this problem was helpful for you guys in thinking about how to think through this type of problem. And don't hesitate to ask me questions. I'll be posting these slides afterwards. See you next time.